Every year, the shipping industry spends roughly $10 billion on a substance that does nothing visible from the surface. You see a ship leaving port, you see a dark hull, maybe a flash of red near the waterline, and you move on. That red is not paint. Not really. It is a slow-release weapon aimed at creatures most people have never thought about. And the reason that weapon had to be invented, had to be perfected over 150 years of engineering and disaster, is that without it, a single cargo ship crossing from Rotterdam to Singapore would arrive carrying an invisible passenger load capable of destroying an entire ecosystem. So here is the question. Why does the color red have anything to do with stopping that from happening? Most people who think about this at all land on the same answer. These ships are painted red because red paint resists rust. It seals the steel, keeps the seawater out, protects the hull the same way you would prime a gate before painting it. This explanation feels airtight. Steel and salt water are a famously bad combination, and the underside of a ship is soaking in that combination every second of its working life. Painting it with something protective makes obvious sense. The logic holds together perfectly, which is exactly how you know it is missing the real story entirely. Here is the number that reframes everything. A single square meter of unpainted ship hull left in warm seawater for 12 months can accumulate up to 150 kilograms of biological growth. Not corrosion. Life. Barnacles, mussels, tube worms, algae, slime bacteria, and dozens of species of organisms that do not care at all about your shipping schedule. 150 kilograms per square meter. A mid-sized container ship has roughly 3,000 square meters of underwater surface. Run that math, and you are looking at the biological equivalent of stacking 2 fully loaded cement trucks onto the bottom of the hull over the course of a single year at sea. This is what nobody tells you. The red paint is not there to stop the ocean from eating the ship. It is there to stop the ocean from growing on the ship. And those two problems require completely different solutions. Corrosion is a chemical fight. Biofouling, which is the technical term for what happens when organisms colonize a hull, is a biological war. The stuff underneath modern ships is not paint in any conventional sense. It is an antifouling coating, a matrix of biocides, self-polishing polymers, and controlled-release chemistry that has been tuned over generations to make the hull surface hostile to life without poisoning the entire ocean in the process. The red color is a side effect of the copper compounds inside the coating. Copper is toxic to the larvae of barnacles and algae spores. When those organisms try to settle on the hull, the copper kills them before they can grip. The coating slowly dissolves in seawater, continuously refreshing the toxic surface. A ship moving through the water at cruising speed polishes its own hull, wearing away a micron-thin layer constantly, keeping the copper exposure consistent. The technical name for this is self-polishing copolymer technology. And it is the reason a ship can cross the Pacific and arrive with roughly the same drag coefficient it had when it left, because drag is the hidden catastrophe here. Biofouling does not just look bad. It destroys fuel efficiency in a way that would be unacceptable in any other engineering context. A hull covered in barnacles increases hydrodynamic drag by anywhere from 20 to 40%. That means a ship burning 300 tons of fuel oil on a clean hull voyage burns between 60 and 120 additional tons on a fouled one. Multiply that across the roughly 50,000 commercial ships currently operating globally, and you start to understand why the marine coatings industry is the size it is. The anti-fouling paint is not a cost. It is a fuel savings mechanism that pays for itself within weeks of a voyage. The origin of this problem is older than steam power. Wooden ships had the same enemy. The shipworm, which is not actually a worm but a saltwater clam called Teredo navalis, bored through oak hulls the way a drill goes through softwood. Ancient Phoenician sailors coated their hulls with tar and pitch. Greek warships were sometimes sheathed in lead. The Romans experimented with lead sheets below the waterline, which worked reasonably well but required skilled labor and added enormous weight. For centuries, the arms race between the sea and the hull was fought with whatever materials were available, and it was always a partial victory at best. When the British Royal Navy began coppering the hulls of warships in the 1760s, it was not an aesthetic decision. It was desperation. Ships were rotting faster than they could be built. HMS Alarm, a frigate sent to the Caribbean in 1761, came back so riddled with shipworm damage that her officers reported the hull was held together more by habit than by timber. Coppering changed naval warfare because it meant British ships could stay at sea longer, needed fewer dry dock visits, and moved faster. Speed and endurance translated directly into strategic dominance. Copper was the anti-fouling solution for a century and a half. Then steel hulls arrived, and copper sheeting became impractical. The industry had to reinvent the solution from scratch, this time in chemical form. By the 1950s and 60s, tributyltin compounds, a family of highly effective biocides, became the dominant technology. As they worked astonishingly well, they also turned out to be among the most acutely toxic substances ever introduced into marine environments, accumulating in the food chain and causing reproductive failure in oysters across entire coastlines. The International Maritime Organization banned tributyltin antifouling coatings in 2008. What replaced them was the copper-based self-polishing chemistry you see today, tuned to be effective without being catastrophic. The red color is the legacy of copper. The engineering is the legacy of every disaster that came before. Once you see the biofouling problem clearly, you start noticing its logic in places that have nothing to do with ships. The slippery coating inside medical catheters is there to prevent biofilm, the same class of problem at microscopic scale. Shark skin, which inspired an entire category of competitive swimsuit design, works partly by creating microtextures that make it difficult for organisms to grip. The reason hospitals use copper door handles and handrails in high infection wards is that copper passively kills bacteria on contact, the same mechanism that makes it useful on a hull. Non-stick cookware uses a surface energy approach, making the surface so chemically repellent that nothing wants to adhere to it, which is cousin to the logic of anti-adhesion hull coatings. The slick surface of lotus leaves, which causes water and particles to bead off completely, has been studied for decades as a model for passive anti-fouling. Bioreactor vessels in pharmaceutical manufacturing are coated with materials specifically designed to prevent microbial colonization during fermentation runs. Even the waxy coating on certain fruit skins is a passive barrier against mold adhesion. The problem of life trying to attach itself to a surface it was not invited onto is one of the most universal problems in biology and engineering. And every time you solve it, you are reinventing what sailors figured out the hard way on the hull of a wooden ship in the Mediterranean 2,000 years ago. The honest limitation of all of this is one that the industry does not advertise loudly. Copper-based anti-fouling coatings work by continuously leaching a biocide into the surrounding water. That leaching is controlled and regulated, but it is not zero. In high-traffic harbors, particularly enclosed ones where many ships sit idle for extended periods, copper concentrations in the water column can reach levels that harm non-target organisms. Seagrass beds near busy marinas show measurable copper contamination. Juvenile shellfish are sensitive to copper at concentrations far below what kills barnacle larvae. The solution that protects the ship is a low-level, permanent chemical release into an ecosystem that did not ask for it. Regulators are aware of this. New generations of biocide-free hull coatings using hydrophobic polymers and foul-release silicone technology are slowly entering the market. They do not kill organisms. They make the surface so slippery that nothing can maintain a grip long enough to colonize it. They are more expensive. They require ships to maintain a minimum speed to be effective. And they are not yet dominant. The industry is in transition. And the red hulls you see today represent a technology that is already beginning to be replaced. And if you think the chemistry of keeping things alive is fascinating, wait until you find out why the concrete in the Panama Canal locks has not been replaced once in over 100 years of continuous operation.